Hey everyone, and welcome to our video on the hypothalamus and pituitary gland. This is sort of one of the nerve centers of the endocrine system, and so quite a lot of important hormones either originate from here or in some way mediated through here. So let's dive into it. Hopefully the background noise isn't too loud. Okay, so in terms of the anatomy, ignore the arrows in the middle. Those are just sort of cut off from where I got the diagrams from. But you can almost consider the hypothalamus and pituitary as almost two different systems. So you have the anterior pituitary system, which starts in the hypothalamus and it goes down through the hypophyseal circulation. It's almost like its own little mini endocrine system. You have your neurosecretory cells up in the hypothalamus. They sort of extend down the axons, and then they terminate on little blood vessels, which then bring stuff down to the anterior pituitary. And in the back, instead of that whole little system, the posterior pituitary is almost like an outgrowth of the hypothalamus. So you can see over there up the top, we have multiple nuclei, which then extend all the way down, and they actually reach the systemic circulation. So that capillary plexus drains into the full systemic circulation. That's not to say that the hypophyseal circulation over in the anterior side isn't part of the systemic circulation. It very much is, but it's a very localized area that really maximizes the ability to get stuff from the hypothalamus to the anterior pituitary cells. And we're going to unpack that a little bit more as we actually talk about these. There's a lot of detail in these diagrams, so you don't need to memorize everything here, but it's good to understand, first of all, that these are two sort of almost separate systems, and then also the differences between them. And don't worry, we will go over them. Yep, okay, so we're going to talk with the anterior system first because it's the more complex / interesting one. So in the hypothalamus, we have what we call parvocellular nuclei, almost like parvo is like little, and they release, we have many names for them, but prepituitary, hypothalamic, hypophysiotropic, they release hormones, basically. So they are neurosecretory cells. They take a neural impulse from higher in the brain, all sorts of stuff, and then they convert it to hormones, basically, that they release into that little hypophyseal portal system, and they start up at the top, and then they go down into the anterior pituitary, where they act on cells there. And like I said, it's like a little mini endocrine system. And then in the anterior pituitary, all of those cells, then they actually go and release their own hormones based on the hormones released by the hypothalamus. Okay. So we typically have some sort of negative feedback to control the system. So sometimes it's going to be direct based on the hormones released by the pituitary. Sometimes those anterior pituitary hormones cause intermediaries or effects, which then regulate the hypothalamus, but there's usually going to be some sort of control to bring it back. And we're going to talk about that specifically in reference to growth hormone a little bit later. One of the consequences of having a really small circulation, i.e. the hypophyseal circulation, is that you can use very small amounts of hormones to achieve the desired effect. So in the systemic circulation, any hormone you release is going to be really, really diluted very quickly because there's just so much blood. Whereas in the hypophyseal circulation, you can have a very small amount of hormone act very effectively on the anterior pituitary. The flip side of that is it's much easier to sort of overwhelm or have disorders when we have an excess or a deficit in hypophysiotropic hormones. Okay, this is sort of a big graph, big table of all of the different steps in these individual pathways. So the first orange row here is in the hypothalamus, the black row is in the anterior pituitary, and the bottom row is talking about their actual effects. Some of these you'll already know, some of these might be new to you. A couple of things I want to point out. First of all, know the acronyms, because sometimes they'll just give you the acronym. It's just assumed knowledge. Also note that some of these are inhibitory. So somatostatin doesn't cause the release of growth hormone from the anterior pituitary. It causes, it inhibits that release. It actually makes less of it get released. Same thing with dopamine. Dopamine inhibits prolactin release from the anterior pituitary. Okay. And we've got all that sort of stuff. I think I was meaning to put in what type of cells in the anterior pituitary produce each of these, but I didn't, so I might go back and add those in. It's not super important though, it's not super high yield. Okay. Okay, so you already know about some of the hormones that we're going to talk about. You might know a little bit about cortisol. We're going to dive a bit more into cortisol and thyroid hormones in future videos, so I'm not going to talk about them too much today. And then luteinizing hormone and follicle stimulating hormone, they're both more sort of reproductive system hormones, so we're going to talk about them next sem when you talk about the reproductive system properly. And then prolactin is just sort of boring because its effects are quite straightforward. So what we're going to spend most of our time talking about today is growth hormone. So we have both positive and negative stimuli in terms of actually eliciting a reaction. So the sort of tip of the spear, the thing that actually causes the change is release of growth hormone, releasing hormone, or somatostatin. But they're in the black there in this little table. We have the actual things that trigger those hormone releases. And therefore, they are the original causes, if not the proximate causes of growth hormone release. So if you sleep, if you exercise, if you are stressed, after a meal when your blood sugar goes down, and if you have certain amino acids in abundance, those things cause more growth hormone to be released, and cause through the release of GIH, RH. And if you have a lot of free fatty acids in your blood, if you have a lot of IGF-1, we're going to talk about that in just a second. It's basically one of the things that growth hormone causes. So this is a form of negative feedback. So you release growth hormone, it releases IGF-1. IGF-1 causes release of somatostatin, which causes inhibition of growth hormone release. And then you have aging and postprandial hyperglycemia. So you've got too much glucose. Now you probably will notice that the glucose there seems a little bit out of place. It seems a bit different to the other things. And you'll actually see that in many ways, growth hormone almost acts like glucagon. And it actually has a very direct impact on metabolism. And it actually acts to counter insulin in a lot of ways. And we'll talk about that. So we get most of our growth hormone, or rather, we get the most growth hormone that we do get in puberty, and then it sort of decreases it constantly until, well, finally end of life. It's most effective from 1 to 2 years to adulthood, basically, like 18, 21 years. And obviously that's the period through which you're actually growing. Okay, so in terms of how it actually does its work, you might have seen like complicated diagrams on the JAK2 and SRC pathways. You don't really need to know the details of those too much. What is useful to understand is the sort of different major effects that it has. So there's some stuff that it does directly and some stuff that it does indirectly. The stuff that it does directly is mostly the stuff over on the right side here, which is the glucose sparing effects. So where we increase lipolysis and we decrease glucose uptake. Both of these things serve to increase the amount of glucose and just general energy compounds in the blood. And indirectly, it actually acts through something called IGF, IGS, and the most prominent of these being IGF-1. And they're called insulin-like growth factors. Sort of a bit of a misnomer as far as I'm aware, because most of them do the opposite. So they actually increase blood glucose, whereas insulin stores blood glucose. So they actually work a lot like glucagon. And so IGF-1 works in the liver, it increases glycogen breakdown, and it causes gluconeogenesis, both of which obviously increase your sugar score. And then in terms of actual growth effects, most of the direct growth effects are actually mediated by IGF-1. So your bone lengthening, more protein synthesis to give you more muscle mass, more cell growth and proliferation, all of that stuff, plus growing all your organs except for your brain, all of that stuff is mediated by IGF-1. So although growth hormone does have important uses on its own and effects on its own, those are mostly metabolic, whereas the stuff that actually does the growing is mostly mediated by IGF-1. And that has implications for when we have a deficiency in IGF-1. So yeah, you can almost think of it as sort of the direct effects of growth hormone. Most of them are sort of on some level about preparing the body to undergo growth, to give it the energy needed, whereas the effects of IGF-1 will often be the ones that actually make use of that energy and turn it into growth. That's not a hard and fast rule, but it is a good overall sort of perspective to have. So in terms of disorders, we have many. Now, if you have too much growth hormone, before you get bone fusion, so while you're still growing, you get gigantism. So if you heard of like Robert Wadlow, who I probably butchered the pronunciation of his name, but he was probably the world's tallest man at some point. And he had a form of gigantism. And so he might have had one of these, a pituitary tumor, which basically just releases lots and lots of growth hormone. And so that causes gigantism because you're just, massively pumping up the amount of growth that you're getting. Keep in mind also that with all the pathways we're thinking about, his body would have been massively reducing the amount of growth hormone releasing hormone that he gets. Because he's getting so much negative feedback through all the IGF-1 that he'll be making in response to the growth hormone. But that's not going to do anything, because even though the hypothalamic impulse to create more growth hormone has dried up, the tumor is just going to make more and more in of itself. And you see a very similar pattern in a lot of endocrine disorders, and you can actually use it to start diagnosing them. So if the body is trying to compensate, but the pathway just isn't working, often it's because of something like a tumor, which just means you just release that hormone, even if the negative feedback pathway is meant to be inhibiting it. And then after bone fusion, because you can't really grow in the typical sense anymore, you instead get things like thickened fingers and just sort of bone thickening and increased mass. So don't tell the endocrinologist, but a lot of endocrine stuff is fairly straightforward in terms of the actual treatment. So we have too much growth hormone. So what do? We give people a lot of somatostatin, which inhibits growth hormone release so that they have less growth hormone. Or we give them receptor antagonists so that their growth hormone doesn't work anymore. Or we take out the tumor so that that doesn't make growth hormone. Basically the treatment for too much growth hormone is find ways to get rid of growth hormone, or find ways to make growth hormone less effective. And to nobody's surprise, if you have too little growth hormone, the treatment is to give you more growth hormone. We're just trying to bring things back to normal, basically. Now, one thing that is quite difficult to treat, in fact, to the point where we don't really have a treatment for it, is what we call Laron dwarfism, which is basically, usually it's a defect with the growth hormone receptors or the proteins that allow it to actually bind to cells. And that's because even if you give them more growth hormone, it won't have any effect on the cells, and it is very, very difficult to repair the cells so that they actually respond to growth hormone. So again, it all has to be sort of broad strokes, but somebody with idiopathic growth hormone deficiency, they're usually kids, and they'll basically look fairly normal, or just like overall smaller, whereas people with Laron dwarfism, they'll be like fully grown, and in many ways they'll look like kids, and not just because they're short, but because they literally have facial features and body structures that you would normally associate with children. And that's basically because they're not getting any of those normal effects of growth hormone. So I know I said we wouldn't talk about the other hormones. Surprise, we actually are talking about all the other hormones, because everyone has something to say about growth. So thyroid hormones, they're good for growth. And if you don't have enough thyroid hormones, you get cretinism, which is another growth disorder, which results in inhibited sort of growth. Glucocorticoids, they're not pro-growth, they're actually anti-growth. If you have too many glucocorticoids like cortisol, you get inhibit growth of all tissues except for your gonads, i.e. the sex organs. And speaking of them, sex steroids like testosterone and estrogen are very important during pubertal growth, because, obviously we think about things like the growth spurt during puberty. And so they stimulate growth hormone release so that you actually get, growth during that period. They make pubertal growth occur in certain patterns, which is why you get stuff like your extremities will tend to grow before the rest of the body. And that's just because of the effect of those hormones and how they interact with the cells in your body. And then they actually terminate that growth by causing bone fusion at the end of it. And so obviously you don't grow indefinitely. So testosterone is pretty simple. It's just if you have no testosterone, that's bad for growth. If you have more testosterone, it's better for growth. For estrogen, it's a bit weird, because if you had low concentrations, that makes it more pro-growth than it would be if you had no estrogen. But if you get to high concentrations, it goes back to being anti-growth. And then insulin, so when I say in utero, I mean in utero. So before the fetus is born, while it's still developing and growing, insulin is a really important factor. And leprechaunism, which I swear is a real disease, occurs when we have defects in insulin receptors. And so the child is born underweight and it just stays underweight because it's not properly getting the signaling required. Okay, and finally, let's talk about the posterior pituitary. So like I said, it's not really a proper gland. It's just where the sort of pseudo gland that starts in the hypothalamus in the supraoptic nucleus and the parvocellular nucleus, where those synapse is the wrong term because they're not synapsing onto another neuron, but it's where they terminate basically. So there is these things called herring bodies, which is basically just you get the nerve terminal of a neurosecretory cell, a neuron, and it's holding a whole bunch of neurotransmitters in so many vesicles, and they all sort of pouch out and form what we call herring bodies. And these are basically the things that get triggered to release when we have some stimulus. So in the supraoptic nucleus, we get cells which release antidiuretic hormone. And so that will be triggered when you're basically losing too much water throughout your urine, typically. So your body will say, oh no, we need to hold on more to, we need to hold on to this more. That wasn't better. And it'll trigger the supraoptic nucleus to release vasopressin. And then, as you guys all know from renal, that basically means that we absorb more water back through the tubules. In the paraventricular nucleus, we release oxytocin. We're not going to talk too much about the effects of oxytocin because you guys, as far as I know, don't need to know too much. I think next sem you might learn about the letdown reflex, which is to do with breastfeeding. Other than that, I don't think we usually talk very much or especially get tested very much on most uses and effects of oxytocin. So suffice it to remember, you get cells in the paraventricular nucleus, they go all the way down and they terminate on the systemic circulation in the posterior pituitary, and then when triggered, they release it straight up. So again, instead of this sort of more complicated system we have in the anterior pituitary, where you have purely secretory cells, like pure glands in the anterior pituitary, we actually have a much simpler system in the posterior pituitary, where the secretory cells are those of the hypothalamus, and they're just going straight into the circulation. So hopefully that clears things up a little bit. Have fun watching the rest of this week's video and have a great day.